So now let's set up the triple integrals to represent the volume of the tetrahedron in the first octant bounded by the coordinate planes and the plane 6x plus 4y plus 3z equals 12. Now notice we're finding volume. Volume is a triple integral of 1. Right, so we're going to set up the triple integrals with 1 with our limits of integration. And I just thought it would help if I reminded you what you should have learned in geometry class, which is a tetrahedron is the pyramid where all 4 sides are triangles. The classic example of which is a D4, right? A D4 has 4 sides and all of them are equilateral triangles, hence it's a fair die, right? But of course a tetrahedron does not have to have the 4 sides be equal. This is just the most common one, or the one that most people know about if they play games. Okay, so let's look at this particular tetrahedron. So we're going to start off by drawing this thing. Okay, so 6x plus 4y plus 3z equals 12. Remember, we've done this before. If you're on the z-axis, that means the x and the y are zeros. So 3z equals 12 would mean z equals 4. And then 6x equals 12 would mean x equals 2. And 4y equals 12 mean y equals 3. So you just connect those points, and there you have your tetrahedron. All right, so we're going to have to do this 3 ways. Let's do the first way the way we know, which is having the region of integration in the xy plane. So then we put a column inside to kind of imagine this. So you've got your column going in, right, from bottom to top. All right, so let's look. So, oh, and let me draw that region of integration. So it was 2 here and 3 here. I'm not drawing it to scale. So this is y and this is x, right? Because this is the xy plane. So this is my region of integration, R. Okay, so volume equals the triple integral of 1. And the way I have this set up is dz first, and then it's, as before, it's up to you which way you want to go. Again, most students are more comfortable with a vertical, which would be dy dx. Okay, so dy dx goes there. Actually, I'm going to do these in all different colors. So let me just kind of do this, and let me put the z's in blue here. dz right here, dy, and then dx I'll do it green. Okay, x is easy. X goes from 0 to 2. It has to be constants, right? Right? Must be constants. Must be constants for your last integral. So that's easy. All right, and actually the z's are okay because z at the bottom would be 0 because it's sitting on the xy plane for that column. And at the top, it's hitting the surface. So I would have to solve this surface for z. So let's think. I bring the 3z over, I bring everything over except the 3z. So 3z equals 12, take away 6x, take away 4y, and then z would be 1/3 times all of that. All right, so that's my z. So I'm going from 0 to 1/3, 12, take away 6x, take away 4y. So then the hardest part is actually the y, which it's the same difficulty we were having in double integrals. You have to come up with the equation of the line here because this is not going to be numbers, right? If it was numbers, this would be a rectangle, right? But this is not a rectangle, this is a triangle. So you have to come up with the equation of the line. Okay, well, y equals down 2 over, or excuse me, down 3 over 2. I remember how to find the equation of a line from algebra class. Slope is rise over run, so -3/2 rise over run, x plus 3. So, and it's starting, of course, at 0. So it's going from 0 down here, 0, up to that diagonal line. negative 3 halves x plus 3. Now keep in mind, this is y equals, this is z equals. You don't have to write them there. They're automatically assumed because of your differentials. And the order of your differentials has to match the order of your integrals, right? In nesting. So the innermost ones, then the next, then the next. All right, there's one of them. So now we're just going to do it again. All right, so that was, this was r in the xy plane. And we're not going to do that one, actually. I'm going to challenge us to do a slightly trickier one. Yeah, I realized the whole page wasn't fitting in, so I zoomed out a little bit. Okay, so now we want to do r in the xz plane. Now, the tetrahedron itself has not changed. So it's still the same tetrahedron it was. It still goes through 4 up here. It still goes through 3 over here. It still goes through 2 over here. None of that is different. What's different is the region we want. So we're going to put it in the xz plane, which is this plane right here. Right? So xz, so now let's draw that region over here. So this is z, this is x. So this is 4, and this is 2. Okay, so there's our region, R. Okay, so now we want to think about our pillars that are sticking in there, right? They're going from a y value over here all the way out to over here, right? So you have your pillars going from that plane over here out and then hitting the surface. So we need this surface solved for y. All right, so that was 4y. So 4y equals 12 take away 3z take away 6x. So y equals 1/4 times 12 take away 3z take away 6x. Okay, so volume equals. So I know my first integral. It's 1, and I'm doing dy first. And y goes from 0, which is where the pillar starts over on this plane, so that's 0, to 1/4, 12 take away 3x take away 6, or take away 3z take away 6x. Sorry, I couldn't read my own handwriting there. Z 6x. There, I was unhappy with my writing, but I made it worse. So what you gonna do? All right, now how do we want to orient this? So we need a rectangle in here, and we can kind of do it whichever way we want. So we can go vertical or we can go horizontal. It doesn't really make any difference. If we go vertical, that would be dz dx. Okay, so we'll do it that way. So dz and then dx. Now x is 0 to 2 still, because constants, no trouble. Z, well, we need to come up with the equation of a line. It starts down here at 0, and it's hitting this line at z equals, the y-intercept is 4. We drop 4 over 2. So that's negative 4 over 2. So that's negative 2 x plus 4. So this is z equals negative 2x plus 4. And remember, this was a y equals for this one. All right, that's another one done. All of these will work. They will all find the exact same area, right? It means same volume. So it's just kind of whichever way you want to orient it will work. All right, let's do it one more time. Let's put R in the YZ plane. Okay, so, and this will be the one we'll actually find. So we have 4 up here. We have 2 over here. We have 3 over here. Same tetrahedron every single time. But this time, we're going to have that back wall be our plane, our region. So when I draw this, this is the y-axis. This is the z-axis. Right? This is the x. This is the z. Right? So 4 and 3. 3, 4. That's where it's hitting. So this is our region of integration right here. All right. So our pillars, they'd be a little hard to draw, but the base is down there, and then it's coming out from that base and kind of hitting the object, right? Hitting the surface. So we have a pillar right there, right? Kind of sticking against that back wall. All right, and then this is our region. So the pillar, it's starting at x equals 0, and it's hitting at this surface, which we need to come up with the equation. Actually, let me do it down here. X equals, well, 6x equals 12 take away 4, y take away 3z. Therefore, x equals 1/6 times 12 take away 4, y take away 3z. All right, so volume equals the triple integral. And this time we're going to do x first. So 0 to 1/6 12 take away 4, y take away 3z of 1. And then we did dx first. And then again, as per usual, it's up to us how we want to orient the last bit. So if we want to do vertical, which is fine, we can do vertical. That would be dz dy. Okay, so I'm going to go dz next and then dy last. All right, y goes from 0 to 3, so that's constant, so that's easy. Z I need to figure out, but again, that's the equation of a line. I did it vertically because we're more comfortable finding the equation of a line this way, with the vertical pointing up axis being our this one we solve for. So that's why I did it. So z equals -4 thirds, -4 thirds x plus 4. So I'm going to put that in -4 thirds x plus 4. I mean, y plus 4. Geez, I don't have an x. This is y. I'm so used to the horizontal axis being x, but it is not. It's y. And then 0 is the bottom because it's down here on the y-axis. All right, this is the one we're actually going to find. So we found setups for the first 3, and now we're actually going to solve for this one. So when we solve this, we know how this is going to integrate. This is going to become x, and then you're just going to stick the values in. I mean, it's kind of that straightforward. So it's the integral from 0 to 3. And then actually we're just going to stick the 1/6 out in front. And then it's the integral from 0 to -4 thirds y plus 4. And then the integrand is just going to become, well, here, let me put it this way. It's 1/6 out in front, and then it's 12 take away 4, y take away 3, z. Right? Because when I integrate with respect to x, there is no x in here. So it's going to become x, and x goes from 0 to this, right? Which is just that. And then I brought the 6th out in front because it's convenient. Okay, now I want to integrate this with respect to z. So there's no z in this, and there's no z in this. So those are just going to be multiplied by z. This one's going to become 3/2 z squared. So this is going to be 1/6 integral from 0 to 3. And then it's going to become 12z, take away 4yz, minus 3/2 z squared, from 0 to -4 thirds y plus 4 dy. So one more step, and then we're going to make Maple do this, right? So this is equal to 1/6 times the integral from 0 to 3. Oops, actually, let me keep my pink, because we haven't done it. The integral from 0 to 3. So this is 12 times -1/3 or 4 thirds y plus 4 minus 4y times -4 thirds y plus 4 minus 3/2 times -4 thirds y plus 4 squared dy. And we are so making computers do this. We are not doing this. No, 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 no. All right, so maple. I'll just put it right here. Maple. We're going to get a solution. All right, so let me go grab my maple. And just FYI, here's the surface, right? So I graphed it. That's what the XY plane shaded. I shaded it gray, right, by putting the 0 in and then shading it gray. But I also actually graphed it in implicit plots. So you could see it with different regions shaded. So that's what the XY plane shaded. This is with the XZ plane shaded. And this is with the YZ plane shaded. It's in the back corner right there. All right, so let's find the integral. All right, so here's the first way I did it. When z was going from 0 to that function, y was going from 0 to there, x, right? And then I did dz dx in the back, and that worked out to be 4. And then I did dz dy, and that worked out. And then I'm checking my by hand work, and sure enough, every which way it comes out to be 4, right? So this would be 4. Now keep in mind, if this was like x, y, z, in meters, just for the fun of it, this would be meters cubed that we found here because this was a volume. And volume is in cubic units.